Now, with this rule by itself, I can get a little extra value out of it. So I was making the assumption that both u and v were growing, right? They're both getting slightly larger. But it's very often that I work with letters that represent constants, right? They don't grow at all. They don't change. Unlike my students, they are stuck in the same place forever. But we can grow and we can learn. So what does this mean for these constant values? Well, if they are not changing ever, then the differential of a constant must be 0, always. Because again, constants do not change. That's what it means to be a constant. So if my u variable is a constant, du is going to be 0. And the formula gets even simpler. Differential of a constant times a variable is just that constant times the differential of the variable. My v du just drops out. It's equal to 0. And let's examine why that is. Like I was saying, if one of those sides isn't changing, then let me go back to my picture. So I'm claiming that the u variable is not changing. That will tell me that this whole vertical line segment here is just gone. The u is not allowed to change. It is only the v that changes. And my formula gets simple. Now, we have not been doing rigorous mathematics yet. We've been talking about intuition. And I hope that's a useful point of view. It certainly is for me. We can already put this to work to try to solve the slope of certain functions. Can't do all of them yet, but we can do some of them. Now, let's take y equals x squared. So my y is my dependent variable, my x is my independent variable, and with this formula, I can actually calculate my dy. My dx is just going to be a dx. There's nothing left to solve there. But I can say that dy should be the same as d of x squared. We put some parentheses in there to make that a little bit more clear. Render faster. There we are. dy is d of x squared. So this differential here is equal to this differential here, exactly because of the rule that governs these two variables. For my rule for calculating this differential, I'm going to say that my u equals x, my v also equals x. So my dy must be x dx plus another x dx. Altogether, it's twice x dx. Now, the slope is going to be my dy divided by my dx. So I set that up, and those dx's look like they're going to cancel, and I get twice x. So that's telling me that the slope of my formula, the slope of my function, actually changes depending on what x coordinate I use. I like that. That makes sense, because my parabolas don't have a constant slope. They get steeper the farther I go out. They get shallower the closer to their root, the vertex I am. So that makes a lot of sense, at least to me, from a geometric point of view. Now, this only helps us with functions that are powers of x for right now. But the intuition that the slope of my parabola y equals x squared should be 2x, that is right on the money. So as we build up a theory of derivatives, our intuition is going to carry us to the correct answer. So I can't do this kind of differential analysis with the sine function, at least not yet. In order to have a more robust theory of calculus, we are going to need to follow the book and incorporate everything that we've learned about limits and continuous functions into this idea of slopes. But I think for right now, this is a good place to stop. See you later.